today's lecture, we're going to transition to a new type of reactor. So the first handful of lectures, we really talked about different types of reactions in ideal batch reactors. And the idea was that we would systematically make the reactions more complicated while keeping the vessel and the mass balances the same, and then figure out different types of problems that we would encounter in different situations in that one reactor. So now what we're going to do is take all the things that we've learned so far this semester and not just apply them to ideal batch reactors, but we're also going to do this to continuously stirred tank reactors as well, or of course, those are better known as CSTRs. And a CSTR operates relatively simply. So you have usually a large vat, often liquid, but not always. And that's filled to some level, and there's an impeller or a series of impellers that try to make sure that the vessel is well mixed. So we have some flow rate in, and then we have some flow that is leaving. Now, the thing that we assume when we're talking about ideal CSTRs are that everything that enters is instantly and homogeneously mixed. Okay, so that's one thing that we're going to assume. The second thing that we often consider is that an ideal CSTR is operating at steady state. Okay. Okay. And so the question that I think of first is, given these new conditions, right, that are much, much different from the operation of a batch reactor, how does this affect the mole balance? Well, remember that our mole balance is just in minus out plus generation minus consumption is equal to accumulation, right? And one of our assumptions comes into play immediately, right? And that's the steady state assumption. So the steady state assumption says, well, there can't be any accumulation, right? Because that is like dNI dt, and any time derivatives at steady state are equal to 0, right? So those go away. So if we think about the rest of the terms here, well, 0 would equal the flow in, and we can do this generically for all of the species. So the flow rate of any species I initially, that's what that 0 will represent, minus the flow rate of that species plus Ri times V, right? And so here's the flow rate of that species in, the flow rate of that species out, and of course the generation minus consumption term comes here. And it's buried in here a little bit, but our first assumption here about everything being mixed instantly and homogeneously, that's included here, right? Because we're going to be able to assume that the concentrations are constant. So for any of those flow rates, right, we can say that that flow rate in is equal to the concentration of that species times the volumetric flow rate. And maybe having VI is not the best notation, right? So because everything would be coming in at one volumetric flow rate that is characteristic of everything in the reactor. Now, the volumetric flow rate doesn't necessarily have to be the same. So my next line won't assume that that's true. So we'll say that 0 equals the concentration of I times the initial volumetric flow rate minus the concentration of species I times the volumetric flow rate plus Ri times V is equal to 0. Now, you might think, why do these two species, or sorry, not species, these two volumetric flow rates not have to be the same? Because we are saying that the reactor is going to operate at steady state. And you might think initially that if that's true, those two have to be equal to each other, because if they weren't, the volume of the reactor would increase over time. Now, for liquids, that statement would be 100% correct. So for liquids at a constant temperature, V0 does equal V in a CSTR. That has to be true. Now, what if we have a gas phase reaction? This isn't something that we'll deal with extensively today, but if we have a gas phase reaction and the number of moles in the reactor or in the number of moles in the reaction change, you have to change the volumetric flow rate, because if A plus B in the gas phase went to C, well, if you kept the same volumetric flow rate out as in, over time you have less moles. And so that would mean that the volume of the reactor would actually decrease. Or if we had the number of moles increase and the volumetric flow rate stayed the same, well, then the volume would get bigger because we're making more and more moles over time. So if we want the volume of the CSTR to essentially be constant, sometimes when we have gas phase reactions, we have to take the difference in the number of moles of reactants into consideration. We're not going to do that today. That might overcomplicate the examples a little bit, but we are going to get into that a little bit later. So for today, we are going to make this assumption that the initial volumetric flow rate is equal to the final volumetric flow rate. And if that's true, then this equation becomes 0 equals CI0 times the volumetric flow rate minus CI times the volumetric flow rate times RIV, okay? And now we're going to divide this equation through by the volumetric flow rate. And we're going to get that 0 equals the initial concentration minus the final concentration plus RIV divided by the volumetric flow rate. And you might think, why do we write it this way? And that's because if you think about this, V has the units of volume, right? So this is volume. And V, script V, has the units of volume per time. And so if you look at this, then those cancel. And you end up with these units that are essentially equal to time. And we don't necessarily think about what's happening in the reactor with regards to the changes with time because it's operating at steady state. But you can then change the average time that a species spends in the reactor. And we call that the residence time. So we actually define this thing tau, which is the residence time, as the volume over the volumetric flow rate. And so if you think that you had a really, really large reactor or a slow volumetric flow rate, the residence time, right, the average amount of time that a species spends in a reactor is very large. And so you might expect that more reaction would happen at larger residence times. Whereas if you had high volumetric flow rates or a tiny volume, the residence time would be low and the amount of reaction that could occur in the reactor would not be as high. And if we insert this term into our mass balance equation, we get that 0 equals CI0 minus CI plus RI times tau for this constant volumetric flow rate, constant volume CSTR. Okay, so that is our mass balance. Now, we don't always think about things just in terms of absolute concentrations. So sometimes we'd like to think of things in terms of conversion. If you remember, we already defined conversion earlier on in this semester as the moles of species I reacted divided by the moles of species I fed. And we define this for a batch reactor as Na0 minus Na over Na0. Well, here, the moles that we're feeding at any given moment in time are a function of the flow rate. And so for a flow reactor, the conversion is actually Fi0 minus Fi over Fi0. Okay, and if we multiply both sides by Fi0, we get Fi0 times the conversion equals Fi0 minus Fi, and we can just rearrange that to find that the number or the molar flow rate at any time is equal to the initial molar flow rate times 1 minus the conversion. And this probably makes sense that if the conversion was 1, let's say, then the flow rate of the reactant of interest would also be 0, right? And if the conversion was 0, it would just be equal to the initial flow rate. So we also could think about our mole balance from up here in terms of conversion. And so we can insert this into there. And if we do that, and let me just zoom out a little bit so you guys can see, we have that Fi0 minus our expression for Fi, which is Fi0 times 1 minus the conversion, plus Riv is equal to 0. And if you look at this equation, so this Fi0 actually cancels with this 1, right? Because this thing expanded is just minus Fi0 plus Fi0 times x. So our equation simplifies a little bit, that Fi0 times the conversion plus Ri times V is equal to 0. And so if we look at this equation, well, we could always solve for the volume directly. Let's say we were asked, find the volume of the reactor needed to achieve a conversion of X amount. Well, then the volume would just be Fi0 times X minus Ri. You also could think about this again in terms of the concentrations, because we know that Fi0 is just Ci0 times the volumetric flow rate. So this could be, Ci0 times the volumetric flow rate times the conversion plus Riv is equal to 0. And we could again divide through by the volumetric flow rate and get Ci0 times the conversion plus Ri times tau is equal to 0, right? And there's a relationship in terms of concentration and conversion where we're still able to calculate the residence time. So what I've tried to do here in the first 15 minutes of class is try to just develop a mathematical baseline for the CSTR. So describe what an ideal CSTR is, and then just give us a couple of equations that we can work with to then solve a couple example problems. The first example that we're going to solve is that a 1 mole solution of reactant A is fed to a CSTR at a flow rate of 120 liters per minute. If only one elementary reaction is occurring, A goes to B with K1 equal to 0.041 inverse seconds, determine the reactor volume and the residence time to achieve a conversion of 0.6. And you'll notice in this example, we've stripped back the complexity of the reaction. So we're back to A goes to B. And again, just like we did in a batch reactor, we're going to systematically increase the difficulty as we go along and solve some similar example problems to what we've done before, but in CSTRs instead of batch reactors. So let's do that in this case, right? And the first thing that we would have done in the ideal batch reactor case is to determine the rate law for this problem. And so we have a problem where A goes to B with a rate constant A1. So what is our rate law for A in this problem?
Negative K1 CA.
Perfect. Thank you very much. And then, of course, then the rate law for B would be equal to just K1 times CA, right? Because RA over the stoichiometric coefficient is equal to RB over its stoichiometric coefficient. And then what we did in the batch reactor case, after we determined what the rate law was, we applied it to the mass balance. And so that's what we're going to do here. And just a minute ago, we derived different forms of the mass balance given our interest, whether it was concentration, flow rate, conversion, etc. So in this problem, if you look at the wording, we're already given the initial conversion. So the thing that we're interested in here then is just to directly apply the conversion version of our mole balance. And that was simply that CI0 times X plus RI times tau was equal to 0, right? That was the result of our derivation. Well, here, let's say for species A, then this gives us CA0 times X plus RA times tau is equal to 0. And if we apply RA, well then CA0 times X minus K1 times CA times tau is equal to 0, right? And that's just applying the rate law to our mole balance, okay? And so if we do that, well, now we have to ask ourselves, well, what is the concentration of A? And we also got that just a minute ago. So remember that FA would be equal to FA0 times 1 minus the conversion. And if FA is just equal to CA times the volumetric flow rate, well, this is just CA times the volumetric flow rate equals CA0 times V0 times 1 minus the conversion. And in this case, in our ideal reactor, right, we can assume that the two volumetric flow rates are equal to each other. And if that's the case, they cancel. And we end up with an expression for the concentration of A, which is just CA0 times 1 minus X. And if we put that into our mole balance equation, we will have we'll have one equation in terms of CA0, which is a constant, and then you have conversion and tau. So if we know one, which we know the conversion, we should be able to calculate tau. So this is CA0 times X minus K1 times CA0 times 1 minus X times tau is equal to 0. And from here, there are multiple ways that we could solve this problem. So sometimes we don't know the conversion, but we know the residence time. Sometimes we know the conversion, we don't know the residence time, right? So every once in a while, you know one, you don't know the other one. In this problem, we know the conversion, we don't know the residence time. So let's solve for that. And if you do, right, you can find that tau equals X over K1 times 1 minus X, okay? So that's one solution to this equation if you know conversion and you're looking for the residence time. You also could solve this equation if you know the residence time and you want to know what the conversion would be, and that would be that X equals K1 times tau over 1 plus K1 times tau, okay? It so happens in this problem, that's the version of this equation that we are interested in, okay? And so we can plug in the numbers that we have. And we know that the conversion is equal to 0.6. Our residence time is 0.041 inverse seconds times 1 minus the conversion again. And that gives us a residence time of 36.6 seconds. So that's the first part of this problem, right? Determine the residence time. The second thing that we were asked to do is to find the volume. Well, we can do that from the definition of the residence time. Remember, tau was V over the volumetric flow rate. So that means the volume of the reactor is the residence time times the volumetric flow rate. And so that's 36.6 seconds times, we're told in the problem that the volumetric flow rate is 120 liters per minute. And now we just have to convert minutes to seconds, right? And we know that in 1 minute, there are 60 seconds. So we can find that the volume of our reactor then is 73.2 liters. So there's our residence time, and there's our volume. And we did this in a very similar way to how we've solved problems before. You find the rate law, apply it to the mass balance equation, solve for the variable that you're interested in. Now, we did this directly in terms of conversion. We didn't necessarily have to do that. And so maybe just as another pathway that you could possibly take to get to the same answer, well, we could, from our initial mole balance, right, FA0, you could go all the way back to FA0 minus FA plus RI times V, right, is equal to 0. And that's CA0 V minus CA times V plus Ri times the volume is equal to 0, or CA0 minus CA plus Ri tau is equal to 0. And we would know what the final concentration of A is, right? So we know that Ca is just Ca0 times 1 minus x, and we know that that's equal to 1 times 1 minus 0.6 from the problem, right? So that would be equal to 0.4 moles per liter. And so tau then is equal to, just rearranging this here, hold on, let me actually insert Ri so I don't skip too many steps. So that's Ca0 minus Ca minus K1 times Ca times tau, right? And of course then tau is just equal to Ca0 minus Ca over K1 times Ca. So that would end up being equal to 1.0 moles per liter minus 0.4 moles per liter divided by 0.041 inverse seconds times concentration of A, which is 0.4 moles per liter. And that would still have gotten us 36.6 seconds. And so hopefully, as we've derived a few equations, looked at this first example problem, there are a bunch of ways here in a CSTR that we could get to the solution, right? We could work with concentrations, we could work with conversion directly. Hopefully, another thing that you've noticed as we've derived a few expressions and worked through this first example problem, that the math is a little easier generally for a CSTR, right? We're just doing algebra right now, as opposed to when we were doing batch reactors, and then later this semester when we'll do plug flow reactors and packed bed reactors, you're solving differential equations. So that is another nice thing about CSTRs, is that they tend to, the solutions tend to be a little bit more straightforward to get to. All right. So hopefully this feels okay. Do you guys have any questions about this before we do the next example? Okay, I don't hear any. So let's move on to example 2. Okay. And example 2 says, now let's feed the exit from the reactor in example 1 to a second CSTR of equal size. Find the final overall conversion. Okay. So this is a CSTR in series problem. And conceptually, what's happening is that we have 2 reactors, right? 2 CSTRs. And we're going to feed to the first one, and then the feed from this one goes directly into there, and then that comes out. So we have some concentration, and again, it's still the same reaction, right? A goes to B with K1 equal to 0.041 inverse seconds. And now we have, CA0 here. We have, we'll call this CA1, and now we have CA2. And we know that if they're the same size, the volumes are the same, the volumetric flow rate is going to be the same throughout, so the residence time for the 2 reactors is going to be equal to each other. Okay, and if we think about this, both reactors, or each reactor, is subject to its own mole balance, right? So we can do a mole balance on reactor 1, right, from here to here. And then we also can do a mole balance on reactor 2, and we can do that from here to here, okay? So let's do that, right? So our mole balance on reactor 1, we had, right, it was FA0 minus FA plus RAV is equal to 0. And this was CA0 times the volumetric flow rate minus CA1 times the volumetric flow rate plus RAV is equal to 0. And of course, RAV is just equal to our rate law. So that's minus K1 times CA1 times V, and that's equal to 0. And CA0 minus CA1 minus K1 times CA1 times tau equals 0. And if we just group terms, right, CA0 minus CA1 times 1 plus K1 times tau is equal to 0. And so we get that CA1 equals CA0 over 1 plus K1 times tau, right? So that's the concentration of A between reactor 1 and reactor 2, okay? Now let's do the exact same thing on reactor 2. Okay, so if we do that, right, obviously the mole balances are going to be the same, except we're just going to replace the coefficient. So this is FA1 minus FA2 plus RA times V, again, is equal to 0. And this is just CA1 times V minus CA2 times the volumetric flow rate minus K1 times CA2 times the volume is equal to 0. And we could divide through again by the volumetric flow rate and get CA1 minus CA2 minus K1 CA2 times tau is equal to 0. And then finally, we could solve for the concentration of CA2. So CA2 equals CA1 over 1 plus K1 times tau. Okay, and if we want to be specific about this, this could be tau 2, and this could be tau 1. Now, in this particular problem, they are equal to each other. So leaving those as just tau is okay. But you don't always have to have CSTRs in series that are equal size. Now, we don't want to necessarily have to measure this concentration all the time. So fortunately, we already have an expression for the concentration of CA1. And so we could insert that into this equation to find the final concentration. So CA2 is then equal to CA0 over 1 plus K1 times tau times 1 over 1 plus K1 times tau. And that equals CA0 over 1 plus K1 tau squared. And the interesting thing here is that if you follow this math, this is really, K1 plus K1 tau to n, where n is just the number of CSTRs in series. So you could do this, 5, 10, 30 times if you wanted to, okay? Now you probably won't ever have 30 CSTRs in series, but hopefully you take the point. So there's our concentration CA2 that is leaving. Well, now what we can do is consider what's happening for the overall process and look at that in terms of conversion, because we were asked what the overall conversion is if we had 2 of these in series. Well, that's still the number of moles of A that have reacted over the moles of A fed, but now we're looking at the entire process. So this is still FA0 minus FA2, right? This is the molar flow rate leaving the final reactor. So the difference between these two are the number of moles reacted divided by the number of moles that are fed. And if that's the case, well, we have FA0 times X equals FA0 minus FA2. And we know that FA2, then, if we solve this, here, forget that FA2 is equal to FA0 times 1 minus the overall conversion. And if the volumetric flow rate is constant, that also means that CA2 equals CA0 times 1 minus X. And the reason that I did that was so I could plug this in to the left-hand side of this equation. And now we get that CA0 times 1 minus X equals CA0 over 1 plus K1 tau squared. And those CA0s are going to cancel. And what you're left with is that the overall conversion then just equals 1 minus 1 over 1 plus K1 tau squared. Okay. And in our problem, we know these, right? So we know that it's 1 minus 1 over 1 plus, and K1 is equal to 0.041 inverse seconds times tau, which was 36.6 seconds. And this whole thing is squared. And so we get that the overall conversion is equal to 0.84. Okay, for two of these CSTRs in series. Okay. All right, so before I ask the next question, is this okay? You guys have any questions about this? Yeah, hopefully it feels like we just applied the same mass balance to two reactors, which is exactly what we did. Okay. So this leads to the question, why would you want to do this? Right? Why do you need two CSTRs in series? Right? Each reactor costs money, and it's probably depending on the system, but you might think that it's cheaper to just buy one reactor than it is to buy two. And so let's ask, well, that's sort of weird, but what would the conversion be if we just used a reactor that is twice as large? Okay, so let's do that. We already did all the math for that. Well, let's do a comparison. So let's say that we had the same volumetric flow rate. So if the volume was equal to 2 times our initial volume, right, that would mean that the volumetric flow rate was the same. Remember, tau is equal to V over V. So if the volume is twice as large and the volumetric flow rate is the same, the residence time is then just 2 times the residence time we had at the beginning, which is just 2 times 36.6 seconds, not inverse seconds, which is just 73.2 seconds. Okay. And so if that's our residence time, well, remember conversion was equal to, we had this expression earlier, K1 tau over 1 plus K1 times tau. So this is just 0.041 inverse seconds times 73.2 seconds divided by 1 plus 0.041 times 73.2. And that means that the conversion is equal to, just solving the problem, 0.75. Okay. And so that means that we have a higher conversion with 2 smaller reactors than we do with 1 larger reactor. Okay. And the question is, why? Right? Does that make sense? So to understand that, let's go all the way back to the first thing that we talked about here, right? And our assumptions about ideal CSTRs. We were told that in an ideal CSTR, everything that enters is instantly and homogeneously mixed. So what ends up happening in really, really big reactors is that as you add a species into the reactor, it is very, very diluted. And that actually drives down the concentration of A. And remember our rate law, right? RA is minus K1 times CA. And so if you're continuously adding A to a larger and larger reactor with a larger and larger volume, you decrease CA. And when you do that, you decrease the number of collisions, right, that are going to happen inside of the reactor. So the overall reaction rate is low. And in fact, the thing to remember about CSTRs, and it's really one of the limitations of them, is that the reactor is always operating at the lowest concentration, right? So you have some concentration, CA0 entering, you have some concentration, CA that's leaving. But remember, if everything's instantly mixed, what is here at the exit and flowing out is exactly the same as what's, and any other point inside of the reactor. So CSTRs operate at the most dilute point. And because of that, making the reactors bigger and bigger and bigger is not a good strategy generally. So if you really need to achieve a high conversion in a CSTR, you are much better off. You are much better off making many, many small reactors. Now that can get expensive. The control of that system can get very complicated. Okay. Now, there is a question of then what the upper limit is, because you think, well, let's just make an infinite number of small reactors. But what would an infinite number of CSTRs kind of behave like? And if you think about that, right, let's just say that we had a really small flow rate, and maybe I won't make them quite this small. Okay, here, let me do this. So let's say that these each behaved as a mini CSTR, right? Well, especially if our volumetric flow rate was low, right? Reaction would happen here, then go to the next one, then happen here and go to the next one, happen here and go to the next one. You spend a certain residence time, right, tau, in each one of those. And really what you're getting to is that an infinite number of CSTRs is like a flow reactor with a very small cross section. And so something we're going to talk about later on in this semester is that really an infinite number of CSTRs would behave a lot like a tubular reactor, where we're just feeding into one side of this reactor and it comes out the exit, right? And because flow exists in little segments or plugs, we call those plug flow reactors. And that tubular reactor we're going to talk about later on in this semester. Okay. So hopefully in lecture today, we at least have a baseline for what a CSTR is, how a CSTR might behave. We also solved a couple example problems. One was a simple one where A goes to B in one reactor, and that's really to familiarize you guys with the math and hopefully feel a little bit more comfortable with it. Then we did 2 CSTRs in series. In the next lecture, we're going to make the reactions a little bit more complex. So we'll do series reactions in a CSTR, we'll do parallel reactions in a CSTR, and we'll also talk about things like yield and selectivity, just like we did for ideal batch reactors.